Hey everyone, in this video we're going to go through these integral problems step by step. And one thing you'll notice right away is that these problems are not all the same type. That was done on purpose. The reason is to show that integration is really about recognizing patterns. Sometimes you use the power rule, sometimes a U substitution, sometimes properties of definite integrals, and sometimes a technique like integration by parts. So the goal here is not just to get answers, it's to practice noticing what kind of integral you're looking at. So let's go problem by problem. So the first problem is we're going to find the integral of x to the power of 4. For this, we use the power rule for integrals, which is shown on the top right. The integral of x to the n with respect to x equals x to the n plus 1 divided by n plus 1 plus c. So that sounds pretty complex. So here, we can write n equals 4, right? That means that we add 1 to the exponent and divide by the new exponent. So the integral is equal to x to the power of 5 over 5 plus c. And that's it. Pretty simple start. The next one, we're finding the integral of 6x to the power of 5 plus 18x to the power of 4 plus 21x to the power of 3 plus 2x to the power of 2 plus 64x plus 521, a pretty complex integral. Now let's move to this longer polynomial. Just like with derivatives, this may look more complicated because there are more terms, but the process is still very manageable. Let's integrate one term at a time. The integral of 6x to the power of 5 is equal to x to the power of 6. The integral of 18x to the power of 4 is 18x to the power of 5 divided by 5. The integral of 21x to the power of 3 is 21x to the power of 4 divided by 4. The integral of 2x to the power of 2 is 2x to the power of 3 divided by 3. And the integral of 64x is 32x squared. And the integral of 521, you just add a variable, so it's 521x. So again, even though the expression looks long, integration is still just term by term here. This one, we're going to find the integral of 4x to the power of 3 minus 7 over x squared plus 9 root x dx. This one is nice because it mixes different power forms. The key idea is that before integrating, it helps to rewrite everything using exponents. Now let's integrate each term. So, the first term, the integral of 4x to the power of 3 is x to the power of 4. The integral of 7x to the power of negative 2 is okay, so derivative of 7x to the power of negative 2 is just going to be 7 over x. And derivative of 9x to the power of 1/2 is 6x to the power of 3 over 2 plus c. Now we have a composition. So this is a U substitution problem. Whenever you see something raised to a power, especially a linear expression in parentheses, U substitution is a very good thing to check. So let U equal 6x minus 5. Then du equals 6x. So dx equals du over 6. Now let's just rewrite the integral with what we know. So we can write the integral of u to the power of 8 times du over 6. So we can factor out the 1 over 6 to the outside of the integral. Now we can use the power rule. So then we just get 1 over 6 times u to the power of 9 all over 9 plus c. And then we distribute 1 over 6. So then once we substitute u back into it, we get 6x minus 5 to the power of 9 all over 54. Plus c. That's a classic u substitution setup. We pick the inside, which is the u, we convert the integral, integrate it, and then substitute the u back. Let's continue. So this is another u substitution problem, but this time it's with a trig function. So the reason this works is that the derivative of the inside, x to the power of 2, is 2x, which is already sitting right in front of us. So let u equal x to the power of 2. Then du equals 2x dx. That means that the integral is the integral of cosine u du, because the 2x cancels out. And this is much simpler. The antiderivative of cosine u is just sine u. So you're left with sine u plus c, right? And now we substitute u back in, so the answer is sine x squared plus c. This is one of the most common u substitution patterns, a function of something multiplied by the derivative of that something. So then eventually, once you take the derivative, it should cancel out. Okay, let's move on. We're going to evaluate the integral of 0 to 3 of 2x plus 1. So this is a definite integral. With a definite integral, we find an antiderivative first, and then evaluate it at the top and bottom bounds. So first, let's integrate it. We get x squared plus x. Now we apply the bounds from 0 to 3. Which means that we should get 3 squared plus 3 minus 0 squared plus 0. And we're just left with 12. And remember, with definite integrals, we do not need to write plus c, because we're finding a specific numerical value. Let's move on. So this is another definite integral from 1 to e, ln x over x. This one is a little more advanced, but still very clean if we recognize the pattern. We have ln x over x, and the reason that should stand out is that the derivative of ln x is 1 over x. So this is another u substitution problem. Let u equal ln x. Then du equals 1 over x dx. So then the integral becomes, from the integral of 1 to e, ln x over x dx, is just the integral from 1 to e of u du. Now for a definite integral, we should also change the bounds. When x equals 1, u equals ln 1, which is just 0. And when x equals e, u equals ln e, which is just 1. So now we have the integral of 0 to 1 u du. So once we integrate it, we get u squared over 2. And we evaluate it from 0 to 1. So once we plug in that value, we should get 1/2. This is a really nice example of how changing the bounds can make a definite integral clear. Next question. Now we have a integration by parts. This is usually used when you have a product where u substitution does not really simplify the problem. The formula is shown on the top right. For this problem, we're going to let u equals x and dv equals e to the power of x dx. Then du equals dx, and v is just going to be ex. Now plug this into the formula. So then we get x e to the power of x minus integral of e to the power of x dx. And the integral of e to the power of x is just ex, so we're just left with x e to the power of x minus e to the power of x plus c. And if we really want, we can factor our e to the power of x. I'm going to be left with that. And this is a great first example of integration by parts because it shows the structure of the method without getting too messy. So, overall, the big idea in all of these problems is this. Integration is really about recognizing the pattern in front of you. Sometimes it's just the power rule, sometimes it's rewriting expressions with exponents, sometimes it's use substitution, sometimes it's definite integral with bounds, and sometimes it's integration by parts. Once you identify the right method, the problem becomes much more manageable step by step. So when you practice, try not to ask, can I do this algebra? Instead ask like, what type of integral is this? Because that's usually the real skill in calculus. Thank you for listening, and join us next time.